So as usual, let me just, in these last couple of lectures and today I'm kind of telling a little story. So let me remind us all of where we are at. If you remember, we decided that we're taking a probabilistic approach to the description of an orbit, right? So given an initial condition, we define this sequence of measures and I discussed in the first lecture about the importance of limit points in the weak star topology. So we have on X is a metric space, so we have the space of all probability measures. And if we look at the sequence of probability measures, it may or may not converge to some probability measure. It may have several limit points. We are particularly interested in the situation where it converges, because that way then the limit measure is somehow describing the statistics of the orbit, if you remember. So this is our point of view. And we're particularly interested in physical measures, if you remember, right? So if mu is a probability measure, so if mu is in M, which is the space of probability measures, Borel probability measures on X, and then we define the basin of mu is equal to all the measures in M. So there's all the points X in X, such that this sequence, all the initial conditions, such that this sequence converges to mu in the weak star topology, given such a probability measure. In general, this basin may be empty. There's no reason why, if you just take an arbitrary probability measure like the Dirac measure on this point, in general, there may be no initial conditions such that this sequence converges to this measure. But if there is, then this means that this measure mu is telling you something about the dynamics of these initial conditions, right? About the orbits. It's telling you the statistics, asymptotically the statistics of this initial condition. And so we're particularly interested when this basin is big, right? Because that means that this measure is important, because there are lots of initial conditions that are described by this measure. So we say that mu is a physical measure if the Lebesgue measure, so here we assume that we have a bit more structure on the space X. So we assume that X is basically a Riemannian manifold with a volume, which we call Lebesgue measure. And so we say that mu is a physical measure if the basin of mu has positive measure. That means there's a lot of initial conditions that are described by this measure mu. That's why it's called a physical measure. Okay, just a little recap of a couple of lectures ago. Any questions about this? So one of the first things we showed, so our investigation for this part of the course is guided by this basic principle and the question about, do dynamical systems have physical measures? Can we find the physical measures, right? So by definition, a physical measure is one which is obtained as a limit point of this sequence of measures. And it turns out that these measures have a particular property, and that's what we proved last time, right? Is that any limit point, so any limit measure of this sequence, mu n of x0, is F invariant Okay, this means that the measure of f minus 1 of A is equal to the measure of A for all Borel sets, for all measurable sets. Let's say, okay, for all measurable sets, for all Borel measurable sets A. So what we're going to do today is try to move in the opposite direction, right? So what we saw some examples, several examples of invariant measures, like the Dirac delta sitting on a fixed point or the periodic orbit, or for piecewise affine maps, Lebesgue measure is an invariant measure. So there are many examples of invariant measures. But of course, what we're really interested is going in the other direction, right? What good is it for us to show we're looking for physical measures? So we're looking for measures that in particular are limit points of the sequence. And we say, okay, if a measure is the limit point of the sequence, then it's invariant. But we don't know if a measure is invariant, whether its basin is non-empty, right? What we really want, the invariance is a property that is in many situations checkable, right? It depends only on one iteration of the map. And as we said before, often you can check it just for some, open sets, for some particularly good sets. So invariance of a measure is a condition that can be checked in many cases in particular situations. So the question is, if I take an invariant measure, does that imply that it is the limit of some sequence like this? Okay, so today we're going to explore the amazing properties of invariant measures. And in fact, these were really established very classical results. And I'm going to write first the sequence of results, and then I'm going to discuss them a little bit more in detail. So the first result on invariant measures actually goes back all the way to Poincare. This is sometimes called the Poincare recurrence theorem. And it is in a very general setting. So for many of these maps, you just need X to be, for some of these theorems that I'm going to state, they apply very generally. They do not use any of the metric or even topological structure of this. You just need a measure space. So we have X, in this case, is just a measure space. And we have F, X to X is a measurable map. I mean, you can think of these as metric spaces and continuous maps, it doesn't matter, but the theorem's a little bit more general. Mu is an F invariant probability measure on X. Okay, so this is the setting, simply that we have our measure space X. Okay, we have a probability measure that lives somewhere on this measure space. And what this theorem says is the really amazing, it's a quite remarkable result. So it says that if you take a set A, a measurable set A, then for all measurable sets A in X with mu of A positive, if you take a set of positive measure for mu almost every X in A, so there exists a subset of A of full measure inside A. For mu almost every X in A, there exists some tau that depends on X positive such that f tau that depends on x of x belongs to A. So another way to say that is that almost every point of A comes back to A at some point, at some time. Right? So this might not seem like much, but it's really remarkable, most of all because there are essentially no assumptions except for this relation between the measure and the map. This is given by the fact that mu is F invariant, right? Which is this property here. This is essentially the only assumption. So we don't know anything about the dynamics. We don't actually know anything about the measure either, right? Of course, the measure comes in again in the fact that we've chosen a set of positive measure, and this is a form of recurrence, right? So this set may be very small, it may be very tiny, and what we're saying is that these points, they must come back to this very small neighborhood, right? You might take A to be a very small neighborhood, so you don't know anything about the structure of the dynamics, you know what these points do, but almost every point actually comes back. In fact, there is a stronger version of this result, is that in fact they come back infinitely many times. Okay, I will put that in the notes. It comes back infinitely many times. There's not an immediate corollary of this because you might have that the set of A comes back to some subset that doesn't come back. So there's a little subtlety there. But this is a Poincare recurrence. This goes back to, believe it or not, 1890s. So this is a very classical result. So basically this way of looking at things, although I don't think that at the time of Poincare he really looked at things this way, right? But starting to think about the dynamics using invariant measures goes back well more than 100 years. So I'm going to sketch a proof of this later. Let me write down some further developments first so we get a nice picture of how the results developed. So in the 1930s, we have a really almost astonishing refinement of this result due to Birkhoff. This is in the 1930s. And he says following, we have still the same situation, right? So we have mu an invariant probability measure, mu F invariant probability. And then the statement is the following. For all phi x to r integrable, phi in L1 of mu. So we're looking at this map. We have what's called, sometimes functions like this are called kind of an observable because they give you a measurement at every point in the space. They define some number associated to every point in the space. And then we have that the limit phi in in Fi of x. Write it like this, phi in xi exists mu almost every x0 for mu almost every initial condition. So when you see it like that, it looks a little bit, it's not completely immediate to understand what it means, but let's look at a specific case of phi. Suppose, let me write this as a corollary. Suppose phi is equal to the characteristic function of some set A. Right? So phi is the characteristic function of this set A. Which is an L1 function for any probability measure. Okay, so what do we have? What does this mean? So then limit as n tends to infinity of 1 over n sum I equals 0 to n minus 1 of the characteristic function of A in the point xi So what is this sum here? The characteristic function is a function that just takes value 0 or 1, right? And we evaluate the characteristic function in the point xi. So if xi belongs to A, then this function will be 1. If xi does not belong to A, this function will be 0. Right? So when you take the sum over these n terms, you are basically counting the number of times that you fall inside A. You're exactly doing that, right? So this sum is equal to k if out of the first n iterations, this belongs to A k times, right? And then you divide by n. So we can write this exactly like this. So this is equal to the limit of n tending to infinity of, we can write it like this. We can write 1 over n times the cardinality of the set of I between 0 and n minus 1 such that xi belongs to A. Questions? Interrupt me if there's something that you don't understand. So if you look at this carefully, this is the proportion of times, right? Because what you're doing for each finite n is you have n, you look at the first n points along the orbit. So let me write this a little bit differently. So you look at a point. So you're taking any arbitrary initial condition, x0, x1, x2, x3. You may, sometimes you fall inside A, and sometimes you fall outside A. And if you see this sum, the maximum value of this sum is 1, right? If you are always inside A, then this cardinality of this set will be n divided by n is 1. The minimum cardinality is 0. If you're always outside A, then this is 0. This is n. So this here is a number between 0 and n, which is exactly the proportion of times that you've fallen inside A, right? If n is equal to 1 million, and you look at this value, and it's a half, so half of the times, so you've fallen in 500,000 times, divided by 1 million is 1/2, so half of the times. So this value here is exactly the frequency of visits, or the proportion of visits. You look at the first 1,000 digits and you say it's spending half the time in A. You look at 1,000,000 digits, this is, again, very similar to the coin tossing that we were talking about, right? And so the fact that this limit exists is absolutely non-trivial and amazing and almost unbelievable, really, if you think about it, right? So what this is saying is that for almost every point, not just, you don't choose an initial condition very carefully, you take randomly, for almost every initial condition, you look at its orbit. Sometimes it falls in A, sometimes it falls inside A. But the amazing thing is that as you take n larger and larger, the proportion of time that you spend in A converges to a very specific proportion, right? So in the limit, it might converge to 1/3 or whatever. It means that 1/3 of the time you're inside A. Okay? So this is just a little bit more general. This is very useful. It's a more general statement for any phi, but intuitively you can think of phi as being the characteristic function, and so what this implies immediately is that the frequency, the proportion of time that it spends in any set, right? So you take any measurable set and you take almost every point and the frequency will converge. So the obvious question is now, converge to what? Is it too much to ask what it converges to, right? Already the existence of the limit is really extraordinary. Can we say what it converges to? It turns out that we can do that under some additional assumption. So this is actually also by Birkhoff. In fact, these two theorems that I'm writing here are usually stated as one single theorem, and I will explain later why I separate them. So we have the same assumptions. Mu is an F-invariant probability, and we add one assumption. Mu is an F-invariant, and now I will introduce a concept which I will not yet define. It's just an additional condition on the measure, which is called ergodic. I will give the precise definition later, probability. Yeah. Okay. Then, for all phi in L1 of mu, so we already know by the invariance that this limit exists. And the amazing thing here is that we know what this limit is. This limit is exactly equal to the integral of phi . Which is, if you can interpret this as the average value of phi with respect to the measure, right? So if you look back at this, let me draw the picture again here. So we have our map f of x to x. We have mu, which is now invariant and ergodic. I will say what ergodic means. We take an observable r, phi, and we take an initial, okay, so this is for almost every, this is for mu almost every initial condition x0 in X. It's not true for every point. We will see many examples to see that it's not true, but for almost every point, this is true. So we take an initial condition here, x0. We look at its orbit. And what this is doing here is it's looking as what sometimes we call the time averages of phi along the orbit, right? So we have this function phi that tells you for each point in your space it assigns some value. We think of this as a kind of measurement of some value. It tells you there's some value. And then you look at the orbit, and the orbit visits different places in your phase space. Depending on where it is associated, phi associates a certain number, right? And we take the averages of these numbers. These are called time averages because you take the average along the trajectory. And this is sometimes called the space average of phi because, as you know, the integral can be thought of in some sense as the average value of the function, right? It's the value that the function would take if it was constant but had the same integral, right? So this is sometimes called the space average of the function. This is called the time average. So this is sometimes called Birkhoff's ergodic theorem, right? And it says that for any L1 function, for almost every point, for almost every initial condition, the time averages converge to the space average. Fundamental result. And we have here, of course, the corresponding corollary. So if phi is the characteristic function of some set A, then just like we had before, what this says is that the limit of 1 over n and the proportion, so the proportion of times when xi belongs to A, right, as we said before, this actually corresponds to this. And what this converges to, by this theorem, well, now we know not only that this proportion converges to something, but it converges exactly to the integral of the characteristic function A d mu. And the integral of a characteristic function is exactly mu of A. And what this means is that if we take the set A here, and the measure of A is 1 over 10, this measure is telling us that almost every point will spend 1/10 of its time in A. Right? So we have been able to obtain an incredible amount of information about the statistics of almost every point, as long as the measure is invariant and ergodic. Right? There's some kind of miracle, and the ergodicity, as I say, invariance is a natural condition which we've discussed already. Ergodicity is an additional assumption that I will talk about, but here I want to emphasize this sequence of results culminating in this one. And there is a further corollary. Yes, so any questions about this before I go on?
Does these theorems has any relation with the strong law of large number?
Yes, this is exactly the strong law of large numbers. Well spotted. This is really strong law of large numbers. It says that when you have very large n, your frequency of occurrence of this particular phenomena will converge to the measure of A. Yes, in probability theory, I'm not sure exactly how the law of large numbers is formulated, because there is a lot of kind of overlap in the results of ergodic theory and probability theory, but often you use slightly different language and slightly different setting. One of the main differences is that in probability theory, you often tend to assume that everything is random in some sense, right? Everything is in a little bit more abstract setting, whereas in this case, in some sense, the ergodic theory is a little bit more challenging, because we are really dealing with a deterministic system, right? We're not dealing with a random system. We're like when you toss a coin, right? Then when probabilists look at this phenomena, they kind of set it up already so that it's a random system, okay? Whereas the actual process of tossing a coin is deterministic, because you are actually applying a force, right? And the consequence of the outcome, if you get heads or tails, actually depends on how much force you apply, right? So if you could control, part of the reasons why coin tossing is so unpredictable is because of the mechanism that we use for tossing the coin, which makes it very, very difficult to control exactly how much force you're giving, right? If you put a little machine, if you put a coin and you put a little machine to toss a coin, and this machine always gave exactly the same force in exactly the same point, you would get exactly the same outcome for the coin, right? You would not get the unpredictability that you get when we toss a coin with our hands. So tossing a coin is a physical process which is deterministic. It's not intrinsically random. And this is the same thing when we're talking about these systems here. We're now introducing a language of probability theory, but we must not forget that we're studying deterministic systems. So this map, F, that we have on x to x is a deterministic system. So the trajectory of this initial condition is completely determined by the initial condition, right? You have the initial condition, you iterate the map, and you don't have any randomness in the system. But it turns out, I guess you could in some sense describe the power of ergodic theory, and we shall see in some of the applications, these are abstract results, that the power of it is that sometimes you can draw some more interesting and very, very detailed conclusion if in some sense you pretend that it's a random system, which is a little bit what we're doing here, right? But the result is even more remarkable because it is a deterministic system, right? And it just turns out that deterministic systems like 10x mod 1, if you remember right at the beginning, we introduced this notion of sensitive dependence on initial conditions, right? So when you have a system with sensitive dependence on initial conditions, it turns out that there's that phenomena that often makes the system more interesting to study from probabilistic viewpoint. It is exactly very, very close to, again, to the coin tossing, and the coin tossing as a physical phenomena has sensitive dependence to initial conditions, right? Because when I say that we cannot control the force, of course, we can control it, but we cannot control it very precisely. If you imagine a coin that you toss maybe 7 or 8 times, that flips 7 or 8 times, right? Then everything depends on the force. If you flip 7 times, you will get heads. If you flip 8 times, you get tails. But the difference in force that you need between flipping 7 and 8 times is very small, and so we cannot control with that level of detail, right? It's got sensitive dependence on initial condition in that sense, is that the initial condition is how much force you give to it, and if you give a little bit more force, it will flip to tails instead of heads, and so you get a different outcome, right? And as we shall see, many systems that we study have exactly this property, especially the systems that have sensitive dependence on initial conditions have a very complicated topological structure, and it's very difficult to understand orbit by orbit what happens. But it turns out that when we will apply these kind of techniques, the idea of finding a physical measure, even though they have sensitive dependence on initial conditions, so if you make a small mistake, you'll get something completely different. What this result says, and this is the amazing thing about this result, is that this property is independent of the initial condition. Almost independent, in the sense that it's true for almost every x. But for almost every x, this limit is the same, right? So we shall see the main systems we will apply will be piecewise affine expanding maps that have sensitive dependence initial condition. So what this means is that if you take a different, a very nearby point y0, right, then it will tend to move away. These 2 points will not stay close together. So after a very short, relatively short amount of time, this will be doing something completely different. But if you look at the statistics, they're doing exactly the same thing, right? They are both spending, if you choose a set, both y0 and x0 will spend exactly the same proportion of time in A. But you don't know when they will be in A. But you know that if you look for a very long time, the amount of time spent will be similar. This is there's lots of applications, or at least lots of conceptually, a lot of connections with the real world in this kind of situations, because in the real world we have lots of systems that are chaotic. One of the most typical examples is the weather. I think 2 days ago, if they told you that it was going to snow today, you'd think this is completely crazy. 2 days ago it was basically summertime, right, in Barcola. And today it's snowing. So one of the difficulties, although to be fair, they did predict. They were able to predict that it would be this kind of weather today. But often one of the reasons it's very difficult to predict the weather more than 4 or 5 days in advance, in fact it's almost impossible, is because the weather is a typical system that has sensitive dependence on initial conditions. So the models look at the weather as the evolution, a dynamical system that evolves in time, and they understand the physics of this system, right? But you need to, even though you know the physics of this system is a bit like saying what is the map, right? The map is kind of the law that tells you if today you're here, tomorrow you're going to be here, right? Or in 1 hour you're going to be here, then you're going to be here, and so on. But even if you know the physics perfectly, you also need to know the initial condition, right? And the initial conditions means that you need to make a measurement, a very precise measurement of the weather, of the parameters that control the weather, the temperature, the pressure, whatever all these parameters are. And of course, you cannot know these initial conditions perfectly because nobody measured these characteristics exactly outside the ICTP building, right? So nobody knows exactly that measurement there or everywhere else. So inevitably, when you have a model, you're starting with an initial condition that is not exactly the correct initial condition. And because of this sensitive dependence on initial condition, in 1 week, your model might tell you that in 1 week it's going to be a hot sunny day, and in reality it's going to snow, like it is today, or vice versa. On the other hand, if you look at the long-term weather, it is very stable, right? If you look at the statistics of the weather, that you always find, so what is the average amount of rain that falls in Trieste in January? What is the average temperature in Senegal in July, right? The averages are very, very, very stable, right? And the averages really means this, the average, right? So it doesn't really matter what the initial conditions are. When we say that the average rainfall in Trieste in January is something, we don't know if it's going to rain, all of this rain is going to fall on the 1st of January, or it's going to be spread out, or which day is going to rain. But we know the averages, right? And they're so stable that when there is a change in the average, it's a big deal, right? So global warming, when they say, okay, the average temperature is 1 degree higher in the world, that is a major, major change, right? That means there's a huge amount of additional energy in the system because the averages tend to be very stable, right? So these are the kind of real-world phenomena. Now, it's not that easy to take these results and apply them to real-world phenomena. What we're going to do in the remaining part of the course is try to understand this in some simple mathematical models, right? But the part of the reason why these theorems are so interesting is because they really truly have interpretation and meaning in the real world. Okay? So this was just a little 5-minute philosophical parenthesis here. Are there any other questions on this before I move on?
Professor, I have one more question.
Yes.
Is there, can you give an example for a system that is totally random? Because it seems like everything is deterministic if I have an external factors.
Well, this would take us into another philosophical discussion, right? Because it is not clear to me what randomness, if randomness exists, really, anywhere. I think that's a very interesting question. As someone who has worked, my thinking, my conceptual thinking, my professional thinking comes from this field. I have learned that we have many deterministic systems that basically behave just like random systems, right? Some of the examples we will see. And these theorems tell us that indeed, in some sense, formalize this idea, right? So the sensitive dependence, what do we usually mean when we think of a random system? When we think of a random system, we more or less think of the properties of tossing coins, right? So we think of something where you cannot predict what's going to happen next, but you can predict the averages, right? The general idea of what randomness means usually contains those two things. Usually we emphasize the fact that it's unpredictable, right? But in general, it also contains the fact that that on the long term, the statistics are quite predictable or quite stable, right? There's, of course, a different level that you might call even more chaotic or even more random, which I mentioned a few weeks ago, where even the statistics do not converge, right? Or I mentioned a couple of weeks ago, which is exactly when these averages do not converge, then depending on your time scale, you have different frequencies, right? So now I will try to make the link with our initial result. But just to begin this link, keep in mind that the fact that this proportion converges, right, is along the direction of that when you toss the coin, even though you have this unpredictability in the short term, not only in the long term is well defined, but the longer you toss the coin and the more you will converge towards 50-50% heads or tails, right? It's, and this is what this is saying also, that what do we mean when we say that I toss a coin, I have 50% probability of getting heads and 50% probability of getting tails? It does not really have a precise meaning, right? When you look at the coin, you don't know. You toss the coin once, there is no meaning to the fact that you have 50% chance heads or 50% chance heads. We give this meaning to a single toss through the fact that we know that if we toss 1,000 times or even 100 times, we will get very close to 50% heads or 50% tails. So that is usually how we use the word probability, right? And in fact, the word probability is used in everyday news all the time, and you have to be very careful about what is meant by this, right? But you're assuming that somehow this convergence happens, right? Because if we have this situation, if we have this conclusion, then for almost every initial condition, the frequency of times, the proportion of time it spends in A is equal to the measure of A. So we say that if we don't know where we are, we take this initial condition, we iterate it 100 times, we have no idea where it might be, but we say, well, with probability 1/10, it belongs to A. Because we know that after 1,000,000 times, 1/10 of the time it will belong to A. So if we have no idea where it is, then we can talk about the probability of it belonging to A, which is exactly the probability of A in the sense of the measure of A for this probability measure, right? So this thinking of this measure mu as a probability measure also in terms of the language, and saying that the measure of the set A is equal to 1/10, in this theorem, the importance of this theorem is says that this idea of the measure describing the probability of the set A actually coincides with the dynamical meaning of probability, that if you don't know where the point is at some point, then it belongs to the set A with probability 1/10. Right? So going back to your question about whether there exists a random system, I don't know if you meant as a mathematical model or as a real-life model. As a real-life model, I would be tempted to argue that every system is deterministic, probably, right? Even physicists sometimes say, well, what about quantum mechanics? Even quantum mechanics is not completely clear. You know, where you just have probabilities of things being in a certain state. As far as I know, but I'm not a physicist, there's no real contradiction to the possibility that there may be some underlying deterministic system, even in the quantum level physics. So certainly what we're studying here from a mathematical point of view is the fact that deterministic systems can be very effectively described using the language and techniques of probability theory. That's what we're going to do. Okay, so before we have a short break, let me just go back now to our original question. Well, I just want to conclude one more corollary, and I want to emphasize a very subtle point of this, which is not often highlighted, which is that the way this is formulated and the actual statement, this set of full measure, what this says is that for all observables phi, there exists a set of full measure for which this limit holds. A priori, this set of full measure depends on which function phi you choose. So this statement does not say there exists a set of full measure such that for every phi in L1, this holds. The difference is subtle, but it is relatively important. In particular here, this holds for mu almost every point, like this convergence. So this is for mu almost every initial condition, x naught. But this set of full measure for which this holds may depend on your set A. Now it turns out that we can fix this if we choose continuous functions and if our space has a little bit of regularity. So let me write this also as an important corollary, is that if M if X if L1, if there exists, how should we say? There exists countable dense subset of continuous functions L1 of mu. So if L1 of mu, so this is a little bit of a technical property, but it turns out that if in most cases, so this can be reduced to a property on the space X. So if X, e.g., for example, if X is compact Hausdorff, topological space. So under some additional conditions on the space X, then what we really need is just this countable dense subset of continuous functions, but this always happens if X is, for example, if X is a Euclidean, is the unit interval, for example, then we have that, then there exists set, let me call it X tilde in X with mu of X tilde equal to 1, such that limit as n tends to infinity of 1 over n integral phi, sum phi xi equals integral of phi d mu for all phi continuous. So the difference, so this, the corollary of Birkhoff's ergodic theorem, so I'm using the same assumptions, and I'm saying, okay, in principle, when you take an arbitrary L1 function, then you have some set of full measure for which this limit exists. If our set X has some natural, has some natural conditions, for example, is the unit interval or the unit square or whatever, then you can find a set X tilde which has full measure, for which this holds for every continuous function. So now, instead of choosing the function and then choosing the set of full measure that depends on the function, we have a set of full measure that is independent of the function. Okay? And the reason why this is useful, and we restrict ourselves to continuous function as opposed to L1 functions. But the reason why this is interesting is because some of you will notice that what this means, in particular, so this means that if you think of the convergence, okay, I will not give the statement, but this I will not give the steps in the proof. I will leave them in the notes. But here we have that what this means is that 1 over n sum of delta xi, I equals 0 to n minus 1, converges to mu. In the weak start topology, right? So this is for all x, for all initial conditions x0 in x tilde. So if you think about what this convergence means, the fact that you have this for every continuous function means that these Dirac delta averages that we're looking before converge exactly to the measure mu. Okay, you can write this sum in these terms here. And so what this means is that this holds for all x0 in x tilde, all initial conditions in x tilde, which means that it holds for a set of full measure of mu measure 1. So this implies that mu of B mu is equal to 1. Okay, maybe this is a really important state. Can you see this? Actually, maybe you cannot see it. Let me write it in a little bit more prominent place because this is important. Okay, let me write it here. Okay, so the conclusion of this, okay, wait, let me take a little bit more space because I want to write one more corollary after this. Okay, so what this says is that mu of B mu is equal to 1. Right? So, in particular, remember the initial problem that we had is the basin non-empty, right? So we choose a measure mu, and we want to know, okay, are there any initial conditions that converge to that measure mu? And the conclusion of this sequence of theorems is that yes, if X is a compact Hausdorff space, which is a very natural condition, if mu is an invariant ergodic probability measure, okay, then the basin has full measure. So almost every point with respect to that measure, if you take the Dirac delta averages, it will converge actually to the measure mu. Right? This is the culmination of this sequence of results, which really are classical. They go back almost 100 years, but they're really amazing. And they provide the foundation results of all the studies that, that we're going to touch the surface a little bit in these next few lectures that use this. So before we take maybe a few minutes break, let me just say that what we really want is a physical measure, right? What's the difference between this property and having a physical measure? Does this imply that mu is a physical measure?
No, it's Lebesgue measure. If mu is Lebesgue measure, then it's clear.
Exactly.
But mu is not Lebesgue.
Exactly, very right. So what this says, this is really the conclusion that is most important for us from all of this that I've just written on the board, okay? But I've emphasized how amazing it is. Now I just want to mention also the limitations of this result, right? Is that everything depends very much on mu. For example, if mu is the Dirac delta on a fixed point, right? Remember that one of the examples of invariant measures were Dirac delta on a fixed point. I've not defined ergodic yet. I will do it after the break. But if it's an invariant measure on a fixed point, everything here is true, but in a kind of trivial way, right? Because if mu is the Dirac delta on a fixed point, then when we say mu almost every x, all it refers to is that fixed point itself, right? Because when you say a set of full measure, it means that if you take any set that has zero measure, you cannot draw any conclusion about that, right? So that's another difference between, so in abstract ergodic theory, you don't have Lebesgue measure. In abstract ergodic theory, you prove these various results, depending on a certain measure mu. But in our setting, when we're interested in physical measures, we are starting with a manifold, we're starting with Lebesgue measure, so we're starting with a reference measure, which is what we're interested in, and we can apply all these results, but the effect of applying these results depend on which invariant ergodic measure we choose. And as we saw also in the examples last time, even if you take something like 10x mod 1 or 2x mod 1, there's lots of invariant measures, right? In that case, Lebesgue measure is invariant, but also you have the Dirac measures on the periodic points and on the fixed points, and as we shall see, there's many others as well. So the conclusions of this depend how interesting the conclusions are, depend on the characteristic of the measure. And as Milmukshin correctly said, if mu is Lebesgue measure, then we actually have that Lebesgue measure is equal to 1. But it does not need to be Lebesgue measure. In fact, corollary, so if mu is invariant, ergodic, and mu is absolutely continuous with respect to Lebesgue measure. So absolutely continuous means that if you take a set of Lebesgue measures 0, it implies that mu of A equals 0. This is the definition of absolute continuity of these measures. Okay, you can easily check that from this. If mu is absolutely continuous, then the definition of absolute continuity also implies that if mu has positive measure, this implies that Lebesgue measure, so if A has positive measure with respect to mu, then it also has positive Lebesgue measure, right? Because if it had 0 Lebesgue measure, it would have to have 0 mu measure, right? So this means that if this set has positive mu measure, then it also has positive Lebesgue measure. So this means that Lebesgue of the basin is positive, and this implies that mu is a physical measure. Okay, so the final corollary of this, which follows very easily from this is the kind of the main result, is that this is true whenever mu is invariant and ergodic. If you add the absolute continuity, then this implies that Lebesgue measure of the basin is positive, and so we have a physical measure. Right? So we have completed, this is what I wanted to tell you, is that our approach was very promising. So we started with looking at the Dirac averages and noticing that every limit point had to be an invariant measure, okay? And then you say, okay, we look at invariant measures, looks like a promising class of maps, and we see that they satisfy some remarkable properties. If you include ergodicity, then it turns out that you can show that the basin is non-empty and in fact has full mu measure. And if you add absolute continuity, you have a physical measure. So there are also other situations where you get physical measures where you do not have absolute continuity. For example, if you have a contraction map, then the Dirac delta is just on the attracting fixed point. So in that case, this Birkhoff's ergodic theorem is not very much good, but you don't need it because you know that all the orbits converge there, so that's also a physical measure. Right? So these are the two extreme kinds of physical measures. One where you have a Dirac delta on an attracting fixed point, another one where you have an absolutely continuous invariant ergodic measure. And then there's also some more kind of combinations of these two, which in higher dimensions, which get a little bit more complicated. But for the rest of these lectures, we're going to use this as a criteria to construct physical measures. And after the break, I'm going to talk a little bit more about these results here. And then for the next few lectures, we're going to look at examples of systems for which we can prove that they have invariant ergodic and absolutely continuous invariant measures. Okay, I've gone a little bit longer than I thought. Let's just take just a short break. Let's take a 2-3 minute break, 3-minute break, yeah? It's 15:08, so let's just take 3 minutes and have a glass of water. Okay. So I think what I would like to do, in terms of the proofs of these results, let me say that the Poincare recurrence theorem is a very simple proof. I will put it in the exercise. It's literally just a couple of lines, remarkably, but it's very simple. I don't think there's any need to do it here. Birkhoff's theorem, I'm not going to prove them. I will give you some notes that have the proof. There are many proofs of Birkhoff's theorem, so these two are usually put together. They're stated as Birkhoff's ergodic theorem. The reason why I don't want to do the proof is simply because, personally, I do not find that it's a bit like magic. I don't find that the proofs are very technical, and I don't know anyone who feels that the proofs has given them some intuition about whether the result is, about why the result is true. So I don't think there's really, at this point, if you want, at some time in your life, it might be interesting to look at the proof of Birkhoff's ergodic theorem. But for the moment, for the purpose of this course, which is relatively short, I think we will skip it. So I think for the rest of this lecture, I want to define the notion of ergodic measure and give a few examples of ergodic measure before we give the applications. So these corollaries, I will give either in the notes or in the exercise. The corollaries are almost immediate, really. It's very easy to see how the corollaries follow from the theorem. So the important thing are the theorems, which I will not require the proofs of these theorems. So the invariance, I stated these two theorems separately because I think it is interesting to realize usually both the theorem is only stated like this, and it is not always clear that the ergodicity is not required for the existence of the limits, and I think that's an interesting point. The ergodicity is only required to be able to say what the limit is. So ergodicity is the following. So definition. So we always have our space. So mu, probability measure. ergodic. For f, right? So we always assume we have some map fx to x. If every a in x, which is fully invariant, f minus 1 of a equals a, then mu of a equals 0 or 1. So the way this is stated, I think it's worth spending a little bit of time carefully on this definition. The way this is stated, so first of all, what does it mean that this set, sometimes we say that this set is fully invariant. So what's the difference? Let me ask you, let's have just a brief discussion about this. So just some remarks. So what is the difference between saying that a set is forward invariant and fully invariant or backward invariant? Can someone tell me what the difference is between these two?
Backward invariant is more stronger. It implies forward invariant, but forward invariant cannot imply backward invariant.
Exactly. So what's an example in which forward invariant does not imply backward invariance? Simple example.
For example, just a quadratic function, maybe.
Yes, so if the map is not invertible, and if you have a fixed point, right, a fixed point for the map is always forward invariable. So if A is the fixed point, if we have P as a fixed point, then f of P equals P, then P is forward invariant. But if a map is not invertible, like in many of our examples, 10x mod 1 or whatever, then there may be several points mapping to P. Right? So this definition here, if the map is invertible, these two are equivalent. In fact, these definitions, you can see, you can easily check that they're equivalent. If the map is not invertible, remember that the inverse is not defined, but we still define this as the set of points x such that f of x belongs to A. Right? What this means here is the pre-image of the set A. So suppose I take the point P, right? P is not backward invariant in a general setting. So I need to take the pre-images of P. So suppose I take A to be the set P and the pre-images of P. Is that now going to be backward invariant? What is the smallest backward invariant set that contains P? For example,
P and its inverse.
excuse me?
P and all elements.
And all what?
All elements that map to P.
After how many iterations? After one iteration?
No, union. Union.
Right.
F minus NP, union of A, but it's ascending chain of sets.
Yes, because then I need to take the pre-images of the pre-images, right?
Yes.
So if I take A is equal to the union over all n greater than or equal to 1 of f minus n of A, for example, that will be backward invariant, right? So here I can, if I take f minus n, so f minus n of A is just the set, of course, of points x, such that fn of x belongs to A. I take all the pre-images. Okay, so this is something I realized recently is actually to understand what a backward invariant set is. Takes a while. So I'm going to put some exercises for you to think about it. It's a very simple concept, but it's actually quite sophisticated at the same time, right? In the invertible case, it's quite easy, but in the non-invertible case, it's not at all easy what this does. And in fact, this is not completely true, that this is backward invariant. When I define it like this, this satisfies the inclusion, one inclusion. It satisfies that f minus 1 of A is contained in A, but to get a fully invariant, f minus A of A equals A, you need to take, okay, in the case of a fixed point, this is correct, but in the case of a general set, you need to take all the images of A and then all the pre-images of the images. So fully invariant set can be quite complex, the structure of a fully invariant set. So there's a very wide variety of fully invariant sets, right? But as Milmukshin correctly said, it's easy to check that if, so note that f minus A of A implies A. Sorry, I want to go a little bit beyond what he said. It's true. It implies also that f of A equals A, but you can check, I will leave this as an exercise, that this also implies that f minus 1 of the complement of A is equal to the complement, right? So what we really have is when you have a set that is backward invariant, so if you have some subset here A, sorry, that is fully invariant like this, so if f minus 1 of A equals A, then we also have that f minus 1 of the complement of A is equal to the complement of A. So what this means from a dynamical point of view is that if you have a fully invariant set and you take any initial condition inside A, then all the forward images, all the backward images of the forward images, any possible thing, any possible point that you can reach from that initial condition by taking forward images and backward images also must belong to A, right? And the same is true for the complement. So when you have this innocent looking condition, this looks like not much, but actually this condition is very, contains a lot of information. And what it means is really is that you have divided your phase space into two completely dynamically disjoint sets. A and the complement of A have nothing to do with each other, right? Every initial condition here, all its pre-image and pre-image stay in here, and the same here, right? So if a measure is not ergodic, what we're saying is that there exists a set which is fully invariant, which has measures strictly between 0 and 1, which means that the complement also has measures strictly between 0 and 1, right? So if f minus 1 of A equals A, and the measure of A is, say, equal to some measure eta, which is strictly between 0 and 1, okay? Then this implies that the complement of AC is also fully invariant, and the measure of the complement is also between 0 and 1, right? Is equal to 1 minus eta, which is also between 0 and 1, and also has positive measure. So that means that we can divide our space into two regions, both of which have positive measure, and neither of which has does not see what happens. Anything that happens here just is not connected to anything that happens here. So it's a kind of decomposable if it's not ergodic, right? So ergodicity is, you could think of it as indecomposability. So there is only really one dynamical system, right? Because if you have these two sets of positive measure that are disjoint, and the dynamics in one has nothing to do with the dynamics in the other, then there's no way that you can get this theorem, Birkhoff's ergodic theorem, right? Because if you take some subset, I'm using now this same notation A, but if you take another subset B here, that is inside A, right? If B is inside A, then all the points that are in the complement of A, they can never visit B, for sure, okay? Whereas the points that are inside A, they may visit B, perhaps some proportion of time, right? So the average, this average here, cannot really be the same. The frequency of visits to B cannot be the same for points in A and points in the complement of A, right? So that's why you need to assume this indecomposability assumption. The fact that it's ergodic is saying that if you take any fully invariant set, it either has zero measure or full measure, okay? So of course, if A has zero measure, its complement has full measure. If it's got full measure, its complement has zero measure. But whichever way you look at it, you cannot write it as the union of two invariant sets of full measure, of positive measure, right? This is the concept of ergodicity, and this is the essential, crucial assumptions in Birkhoff's ergodic theorem. So I will give some examples, although I would like to say that the ergodicity is one of the biggest outstanding problems in dynamical systems, in physics also even, right? So in dynamical systems, you would like to apply, I made it look very simple, like all you need is an F-invariant ergodic measure, and then you get this basin, you get this physical measure, but of course what you need is an F-invariant ergodic measure, right? If possible, also absolutely continuous. But the biggest problem is the ergodicity. So as we shall see, invariance of the measures is in many cases, it's not that difficult. You may even have dynamical systems in which you assume invariance of Lebesgue measure. So area-preserving systems, volume-preserving systems are very natural, even in applications from physics. But in those cases, it is even more difficult to prove that Lebesgue measure is ergodic. In fact, some of the biggest open problems in this area is to show that certain area-preserving systems, Lebesgue measure is ergodic, or volume-preserving system, volume measure is ergodic. So ergodicity is a crucial assumption. If you don't have ergodicity, you might end up being able to split it up into many different ergodic components, even an infinite number or a countable number of ergodic components. So it's fairly easy to show that something is not ergodic. So let's give some examples here. There are some easy systems in which it's easy to show that it's ergodic, right? So let me also emphasize that in this definition, the definition of ergodicity does not require the measure to be invariant as well. So almost always invariance and ergodicity are used together, right? But the definition itself does not need invariance for the definition to hold. So if you have just a Dirac delta in some point, this is always ergodic, right? Why is it always ergodic in any point? Why is it always ergodic? For a very trivial reason, that every set has either measure 0 or 1, or Dirac delta, right? If you take the Dirac delta in one point, then the measure of every set is 0 if the set contains x, is 1 if it does not contain x, right? So every set, so delta x of A equals 0 or 1 for all sets A, all measurable sets A in X. If you take the Dirac delta on a periodic orbit, we see also in or every, so if you are, yes, so if you take the Dirac delta on several points, then of course this is not ergodic. So if you take a measure mu, so okay, let's introduce some dynamics because I don't want to be insistent. So suppose P1 and P2 are fixed points, right? Then Dirac delta P1 is in fact invariant and ergodic, right? Dirac delta P2 is also invariant and ergodic. And what about the measure mu that is sitting half on P1 plus half on P2? So we have two fixed points, P1 and P2, and we take a measure that is sitting half on P1 and half on P2. Okay, I will leave you again to do perhaps exercise on this. But it's quite easy to see that you can find, if you take, like we said before, if you take a, well, if F is invertible, for example, if F is invertible, then P1 itself is a forward and backward invariant set. P2 itself is a forward and backward invariant set. So if you just take the measure of P1, it has measure 1/2, which is something between 0 and 1, which means that this measure is not ergodic, right? If the map is not invertible, you can do a similar things, which I will not do now, but you can see that if you take what we said before, if you take P1 with all its pre-images, right, and its image, then you get a fully invariant set containing P1, and then you take another fully invariant set containing P2. These two sets must be disjoint, right? And one of these sets will have measure 1/2. The other one sets will have measure 1/2. So this again is not ergodic. So in all cases, this is not ergodic. Another example. Sorry, then we will finish. Is example here. Suppose we take this interval map 0, 1. Here we take 1/2. And suppose I define the map like this. This is the point 1/4. The point 3/4. 1. So the slope here is -2. The slope is 2. This is kind of similar to the 10th map or to 2x mod 1, but it's a little bit different because you can see here that Lebesgue measure is invariant. because if you take, it's exactly the same. If you take some set A here, and you look at its pre-image, this slope is 2, this slope is -2. It will have two components, each one of half the length. So exactly as we showed the invariance of Lebesgue measure in 2x mod 1, you can show that Lebesgue measure is invariant, but Lebesgue measure is not ergodic. Why is it not ergodic? Because you can see here that the interval 1/2, so this is 1/2, this is 1/2, 1. So the interval 1/2, f minus 1 of the interval 0 to 1/2 is equal to the interval 0 to 1/2. Right, so the pre-image of this interval 0, 1/2 is exactly the interval 0, 1/2. And the pre-image of the complement, f minus 1 of 1/2, 1. Okay, you can take it open or close here, it doesn't matter really, because everything is modulo sets of measures 0 here. Maybe I should have said that in this setting, you know, everything is always measure 0. We don't really, when we talk about measures, we don't really care about sets of measure 0, so we don't really care exactly about what happens at the boundaries here. But, and you can see, so this is not ergodic. It has these two intervals, 0, 1/2 and 1/2, 1, do not connect to each other dynamically at all. If you take any point in here and you take any of its images or pre-images, it will stay in here, except for this point here, which is right on the boundary. But here, every point here will also stay inside here. If I change the graph, for example, here, in this part, then the dynamics will change only in this interval here, and this interval here will not be able to perceive any of that at all. Okay? So this is an image, this is an example of a non-ergodic measure. This is another example of a non-ergodic measure. What we're going to do in the final 3 lectures is we're going to develop techniques to prove ergodicity in some cases, like in 2x mod 1, right? This is non-trivial, 2x mod 1 and more general full branch maps. And this will then allow us to construct physical measures for those cases. Okay, so before we finish, I just want you to stay on the line and we have a little discussion, but I think we can stop the recording, please. And thank you. And so I just wanted to ask you briefly what you thought, if you got my email. I was thinking, I do apologize for being late, but I think we've been covering a lot of material at a fairly fast pace. So I don't know what your other commitments are, if it would be more convenient for you to continue. If we continue, we have 3 more lectures. There would be one on